Hello students, in this lecture I will discuss about the principles or the concept of water treatment by sedimentation. So you can see there is another name is Stokes formula and application because the thing we are going to study involves some formula called Stokes formula. Let's begin. Okay, there are three types of sedimentation as described in most of the books of water treatment. Type 1, type 2, type 3. These are the three very simple names, but we also need to know the other names because the other names are descriptive names, and in this with this name we can understand what is happening inside. The first one is discrete particle settling. That means every particle is analyzed or settles individually without affecting the other particle, and we can analyze them and we can model them. We can make a formula out of them. And flocculent settling is not like the discrete settling. Flocculent settling, uh, when some chemicals are applied and one particle is attached to another particle, so the settling property will be a bit different and the formula would be a bit different. So flocculent settling. And hindered settling means something is disturbed, hindered. That means it is not settling because of some other matters. In wastewater treatment, there is another kind of settling is described there, that is called blanket settling. So in this particular lecture, we are discussing about only discrete particle settling. And there is another graph here in the bottom. You can see this is I got it from another book. It says the size of particles, and this is a nanometer particle. Okay, this is nanometer, micrometer, and the particles larger than 1 micrometers are suspended. That means they create sediments, and particles smaller than 1 micrometer to 1 nanometer are called colloidal particles, and beyond that, that means smaller particles smaller than that are basically dissolved. We cannot see them through the liquid; they are transparent, and this part is non-transparent. Like when you mix powdered milk in water, it becomes colloids. Okay, and we cannot settle them, we cannot filter them. So for that kind of particle we need different kind of settling, that means flocculent settling. And also in the smaller particles, the larger particles can be analyzed using the discrete particle settling technique. And what is the technique? To understand, first let us see what happens if we drop two particles. One is a very heavy ball and another is a very light particle in vacuum. They will accelerate under gravity and will achieve some velocity when they reach the bottom. Okay, they will reach the bottom together. But if we introduce air here inside, then you will see this particle will reach the bottom and hit the bottom earlier than this one. This will float, and because of the large area it will take time come down. Okay, so that is happening when a particle is settling in a medium. So let's see what happens. This is a particle, discrete particles. That means this is alone, and when it settles, that means something is attracting it. That something is our gravity. So the force generated by gravity is ma or mg. M is the mass of this particle, and mass means the density into volume. This small p denotes particle. Okay, this particle, and this g for gravity. The force exerted by gravity is the density of particle into volume of particle into g. But when this particle is inside some media, that means air or water, in our case we are studying settling, sedimentation for water treatment, so this is water, then a buoyancy force reduces this force. Okay, so Fb for buoyancy force, and this is the amount reduced is the force of same volume of water. That means the weight of the same volume of water as the particle. So volume of particle is multiplied by the density of water, not the particle. This amount is the buoyancy force acting upwards. But due to these two forces, it will generate velocity and acceleration. Okay, force, when there is a force, constant force, it creates acceleration. and it increases velocity. But due to the velocity, there is a frictional resistance that is called drag force. Fd for is the drag force, and the equation is something like this. And here AP is the cross-sectional area of the particle. This is the density of water. CD is the coefficient of drag, and V is the velocity. That means as the velocity increases, the drag force increases by the square ratio of the velocity. So the equation, if we equate these three forces, the equation is like that. And why did I put a equal marks? Because after a while, initially the velocity will increase, the drag force will increase, but the drag force will increase in a higher rate because the velocity increases slowly, but the drag force increases in a square ratio. So soon this drag force will catch up with this velocity inducing forces, and they will be equal, and then there will be no increase in velocity because they neutralize all the force. Therefore there is no acceleration. No force means no acceleration, so the velocity achieved is sustained, and the settling particle settles in a constant velocity without any acceleration. So when we drop something without a media, it has acceleration, but when it drops in a media, especially in water, the soon the acceleration is gone and it settles with a constant velocity. And if we apply for settling particles, most of the particles are sphericals. So if we assume the particles are sphericals, then we can apply some formula like volume is equal to 4 by 3 pi r cube and area of the particle is pi r square, something like that. Then we can reduce this equation to a simple one. And another assumptions is the laminar flow, because when we consider treatment of water, we always flow the water in a laminar flow so that all the flow lines are parallel, no turbulence, because turbulence leading to resuspension of particles. So when the laminar flow, the drag force coefficient will be 24 by Re. This Re is the Reynolds number. Reynolds number have some equations. You should have studied this in fluid mechanics, I guess. And this is laminar flow. For turbulence flow also CD have some expressions, but we don't need them. Okay, transitional or turbulence flow. So if we apply these two things, this equation becomes something like this. And on the left side, Vt, T means terminal settling velocity. This is the velocity. Okay, this is V. That means the velocity increases, and after a certain period, the velocity does not increase. That is the last velocity achieved. Okay, so last called terminal. Okay, so this is in some book it is written as terminal settling velocity. So this is the equation, and you can see rho of particle minus density of particle minus density of water here, and this mu is called dynamic viscosity. Okay, it came from Reynolds equation. Okay, dynamic viscosity. Or if we replace dynamic viscosity with kinematic viscosity, you can see this dynamic viscosity divided by this density of water makes it kinematic viscosity. So if we change it to kinematic viscosity, the equation becomes like this. You can see rho W, that means density of water is divided by density of water, it became 1, and particle density divided by water density makes it a specific gravity. Okay, and in the bottom part, this mu divided by rho W makes it mu, that means kinematic viscosity. So this equation is called Stokes equation or Stokes formula. So how it works, let us explain. Oh, before going to the explain, how do you get rho or mu value when you are applying this equation to a particular particle size? You can get the values from a physical property of water table. These tables are available in all standard books of water treatment. Okay, so for a particular temperature, you can get the kinematic viscosity or dynamic viscosity value, and in between you have to interpolate. Okay. So in a Stokes formula, you already know this is gravity, this is a specific gravity, this is kinematic viscosity. And for a particular settling plan in a particular day of a season, these three things are constant. You see, G is constant for a particular location, specific gravity, because all the sediments are created from sand or stone chips, so they should have same specific gravity. And for a particular temperature in a media, that means water, the kinematic viscosity is same. So the difference is all the particles have different diameters. Okay, so due to different diameters, all the particles will have different settling velocity, because this is a velocity equation. Okay, settling velocity. So velocity is proportional to diameter square. That means if one particle have two twice the diameter, then it will have four times the velocity. So let me illustrate this. This is a small particle. This is the settling velocity. This is a larger particle. Diameter is 2 times, so it has 4 times settling velocity. It settles quicker, much quicker. And if it is 5 times, it is 25 times settling velocity. So just keep it in mind. Larger particles or heavier particles settles quickly. Smaller particles, fine particles doesn't settle. That is why you can see the sand settle in the upstream areas, and the all the finer particles flows down. And this is a popular figure represented in all books, and this is another figure. Okay, this is a large particle, it has higher settling velocity, and a small particle, smaller settling velocity. And but for both particles, when it is in a stream or in a treatment plant, it it also have another velocity, that is called the velocity of the current of this flow. That means the flow velocity, that is horizontal. Vh means horizontal velocity. This is q by cross sectional area, flow rate by area. This is a very popular equation, you know. So both have this, they are flowing with the water current, so they have two velocity components, and the resultant is shown in the red. So these two are the same, but these two are different. So they have different resultants. Some particle will have a trajectory like this. Some particles will have a much vertical or steep trajectory like this, heavier particles. So what happens? We also see this in our day-to-day life. Maybe you are familiar with this thing. The people use this technique to separate the rice or the paddy from the husk. Okay, the lighter particles. They just throw or they just drop the all the particles from a height where in a windy day. Then you need some wind here. Okay, so because of the wind, the lighter particles flows away, and the heavier particles settles here. So thus they separate the light particles without rice and with the heavier particles with rice inside. That means the paddy. Okay, so heavier particles settles here, and light particles with the same velocity. Because of this velocity is low, the trajectory goes there. So this goes here, this goes there. So we apply the same velocity, same technique in sedimentation. You can see the heavier particle settles very quickly if dropped from this point. This is a bit less heavier, so it has a less settling velocity. It also settles here, and this length represents the length of the treatment plant or the sedimentation basin, whatever you say. And this particle, this is even smaller than this, and so slower. The settling velocity is slower than this. It settles in the edge. This particle is even smaller than this, and it has even slowest settling velocity, but it doesn't touch the bottom. It goes out with the water. So if you imagine this is the settling chamber, this means this is not settled in the bottom, so it is not removed from water. It is flowing with water. But what happens even if this particle flows out, other particles, because particles are not like the previous picture shown from the bottom. In a flowing water body, particles are distributed all over the depth, all over the cross section. So all the particles, but if the top particle settles down, all the bottom particles settles down here. Okay, but if the top particle doesn't settle down and flow out with the water, it doesn't mean that all the particles going out. Maybe some particles are entering from this point and they will hit the bottom, because they will have parallel flow lines, because this velocity is the same for everybody, this velocity is same for everybody, so they will have parallel flow lines because of the uh, position of entry. Okay, like this one. So you can see these particles, 100% particles are removed from water, this and this. That means the top particle determines if it is 100% removed. If top particle is removed, all the particles are removed. But if the top particle is not removed, that doesn't mean all particles are not removed. Some portion is not removed. Okay, so how do we calculate this? We will show this, and to describe this thing, to define this thing, we have introduced a new term called surface overflow rate. SOR, surface overflow rate. You can see this velocity, the particle, this is the slowest particle that is 100% removed. Okay, this was 100% removed, this is 100% removed, this is 100% removed, this is not 100% removed. So this is the slowest particle. This is slower, and this is the slowest, but this is not the slowest, which is 100% removed. This is the slowest settling particle, which is 100% removed. So the definition is like this: surface overloading rate or surface overflow rate. You can see I wrote it surface loading rate. Some books write it like this, and surface overflow rate, but the terminology is SOR, not SLR. Some books write it SLR as well. So surface overflow rate or surface loading rate is the settling velocity of the slowest settling particle that will be removed completely. This is not the slowest, this is slowest, but it is not removed completely. So this is among those the slowest settling particle that is removed completely. Okay. So how do we mathematically express that thing? So this is the settling chamber, and this is the cross sectional area. This side, this denotes this side, and this dotted line is here. Okay, this is the dotted line. So this is the triangle. This is that triangle. So what happens? This triangle, this is a smaller shaded triangle, and the larger triangle like this triangle are the triangles with similar angles. Okay, so we can compare, or you can make a ratio of the arms and we compare them because they have the similar arms ratio. Okay, the length ratio. So this arm, that means the v0, divided by this arm, that means the v0 by v, should be v0 by v should be this step, that means h by l. Okay, h by l. Okay, again you can see the flow rate Q is equal to AV, and area means this area, this cross sectional, not this area. Cross sectional area means H into B. So B into H is the area in velocity. So if we want to put this velocity value here, what will happen? This velocity is equal to, if we just change it and then put this value here. Oops, what happened? Okay, we put the velocity value here, and this equation becomes this, and h is cancelled, and the equation becomes like this. So v0, that means the settling velocity, that is called SOR, surface overflow rate, or for overflow rate is equal to Q by BL, and Q is the flow rate, BL. You can say B and L. That is the, especially this surface area, denotes the surface area. So the name somehow becomes surface overflow rate. Overflow. That means overflow, but this is flow rate over surface area. Okay. So how do we use it to detect how much portion of this particle will be removed? Let us see. Here is a particle which have a settling velocity slower than the surface overflow rate. Okay, and how do we compare? So in these two shaded triangles, this triangle and this triangle, we can make this ratio V3 by VH. These two arms, V3 by VH, is equal to H by L. Okay, and here V4 by VH is equal to H prime by L. So H by L, or VH is same, H is same, L is same. So if we put them in one side, then VH by L becomes like this, VH by L. So this two becomes the equal terminology. Okay, V3 by H, V4 by H prime. So if we compare them V3 by V4 or V4 by V3, it becomes, so velocity, this settling ratio of settling velocity is the ratio of depths that is covered. And you can see from this figure, this lower triangle and the upper triangle is the similar triangles. Okay, because these two are parallel lines, and this H prime represents the amount of particle entering inside which are removed in the bottom. Okay, and this H represents all the particles that is entering inside this section. So V by V0 becomes, that means V4 is the settling particle velocity divided by V0 means the overflow rate. V by V0 becomes amount of removed sediment divided by total. That means the removed sediment, this part means this part, actually removed sediment ratio to the total sediment is the actually the ratio of the velocities, surface overflow rate. So if it is half of the surface overflow rate, half of the particles will be removed. If it is 80% of surface overflow rate, then 80% particles will be removed, that means will settle, and 20% will go out. Let us see an explanatory mathematical example which I created. It is not, I think you cannot find it in any books. So you see, in a flowing water body, there are different size of particles, and if we separate those particles, and if we know we mixed 150 milligram or gram particles in 1 meter cube water, and this particle of 200 and this particle of, like a sieve analysis, okay, result is amounts, spelling is wrong, AMOUNT, there should be an N. Okay, anyway, so how do we calculate? We can easily use the Stokes formula. That means something, terminal settling velocity is equal to G into S minus 1 divided by 18 nu into D square. So you can use this formula to calculate these settling velocities for each diameter of particle, okay? And then we can compare, this is the SOR. So if this velocity and this velocity is larger than SOR, so we compare V divided by V0. This is V and this is V0, okay? V by V0, this is the comparison. So these particles are larger than SOR, so they will be 100% removed, okay? So this will be removed within this percentage. V by V0 is the ratio of sedimentation or removal. So this is the multiplication factor to this. That means we have to multiply this 150 gram, not 150 gram will be removed, only 2%, around 2%. 19 means 2, around 0.2. Around 2% of this particle will be removed. So 2% is, oh, if you multiply, you can get this figure. And here about 17% of the particles of this 200 grams will be removed. So about 34 grams. Here almost 48% of these particles will be removed. This is 150 gram. And here all the particles, because the settling velocity is higher than the SOR, so all the particles will be removed. So if we multiply this by 1.9, this will become 190. So that is wrong because we have only 100 grams. So multiplication factor will be 1. 100 becomes 100, 56 becomes 56. So these are the total particles that will be settled. That means removed from water. And among the 836 grams of total sediments, 351 grams or 352 grams are removed. So you can easily calculate the percent of removed particles, okay? That is 42%, around 42% here. So this is a conceptual math, but in the regular math, the things are quite different because we cannot measure like a sieve analysis. So they will have a different technique, but the concept is the same of this concept, okay? Later parts concept. That's all for today's lecture. Thank you very much. You can ask me any questions in the classroom later. Thank you very much.